Antofagasta, Chile, to give us a seminar about the water in mining. So Professor Luis is that famous scientist and professors in that area of mineral processing. He got his PhD in United States, Wisconsin University, and now he's that professors and also that head of the department of mineral processing in the University of Antofagasta. He works about 40 years, 40 years, 30 years in Chile. That's in the area of that mineral processing. Of course, he have achieved a lot of achievement in that scientific technology. Today, he will give us seminars, waters in mining, the case of Chile. Let's have that approach or to welcome Professor Luis. Okay.
Thank you for having me. It's a pleasure and honor to give this webinar. And today I will present our work related to the use of water in mining. We have been working on this topic in the last 10 years. And the main issue is that we use seawater. So most of my presentation will be related to seawater and several problems. The transportation, if we're going to desalinate or not, the problem in mineral processing, and how to manage the water in this kind of system. So let's start by the motivation. Antofagasta regions is in the Atacama desert. This is the dry desert in the world. So sometimes we don't have any rain in 1 year. Sometimes can be 2 or 3 years without rain. Only will be rain in the mountains. So if you look at this region, we have the coast. This is Pacific Ocean. Then we have the coast mountain, and then we have this place between these two mountains, between the Andes and the coast mountain. And so will be some rain during the summer. Snow, actually. Most of them snow in the mountain. So there is lithium water available in the year that comes from this mountain. And most of the activity, copper mines are all around, but the biggest one are around here in the mountains, in the Andes. So the main problem is they need water to operate, and there is not water available. And this region also have several particular issues, like there are a lot of copper and natural sodium nitrate. They are quite unique in the world. So because of that, we are the first production in copper, iodine, natural sodium nitrate, rhenium, but also the second in lithium. And this lithium comes from brine. And molybdenum also comes from the copper industry. Because this is a desert, the sky are very clear, so there are also a lot of astronomic activity and the use of solar energy in the regions. In the country, the mining use about 3% of the water, but in these regions, the mining use about 30 to 70% of the water. So there is a lot of social concern about how this water is used. And today, all new projects have to use water, where they cannot use any more water that comes from the mountain. And these are the mine operation in the region. So you can see there is a lot, but most of these in the coast are medium size, small size, and the biggest are around here. And so it's not only a problem to give water to one mine, but to several mines at the same time. In this map, you can see the demand in blue, the demand of water, and the supply of water for the different regions in Chile. So Antofagasta region is the second one. And you can see here that the supply is very low if you compare with the demand. And the same happened with the third region. And there are these two in the Atacama Desert. And because of that, the companies start to use seawater. They use without desalination and with desalination. And you can see that it has been increasing the use from the 2010. And today, this is about the double, especially the desalinated water. Because to use raw seawater is not easy. We will see that there are several problems. So at the beginning, several companies start to use also raw seawater, but because there are some problems, most of them have changed to use desalinated water. And I guess that you know that in general, for a mineral, we can use a hydrometallurgy process using leaching and this kind of operation, or we can use a pyrometallurgy process. So in the case of copper, that is the main product in our region, usually if we have an oxidized ore, like malachite, we will use a leaching process and solvent extraction and electrowinning. But it is sulfide, like the chalcopyrite, we were going to use flotation and some rusting, smelting, and refining. And the problem is that the concentration plant, this is the flotation plant, use more water than hydrometallurgy plant. And you can see, most of the water is used in the concentration plant. This is for two reasons. First, because for each ton, we need more water, but also because most of the copper has a chalcopyrite. And in the future, the chalcopyrite will increase and the oxidized copper will decrease because the oxidized are in the surface of the mine. And when we go down, start to appear all the sulfurs. So in the future, more water, we will need more water. So let's say that Antofagasta region is in the Atacama Desert and water is scarce. And this is the main activity in the region. So flotation use most of the water. And so this is a social problem with the use of the water. And we start to use seawater. So what are the problems if we use seawater? The first question is if we should use desalination or not. What are the advantages and the problem if we use desalination? The second is the water distribution, because the ocean is here, but cover plants are around here. So we need to pump this water. And the problem is how we can do it, and what are the costs, what are the problems. And then if we use raw seawater, what are the problems in mineral processing? And this in flotation, but also in the water problem. How about the tailing? Because there is a lot production of tailing in the mining. So is any problem with seawater in the tailing? And how about recycling? Because what you can see next in the presentation, water is expensive in this region. And so the company wanted to recycle the most that they can. But if you recycle, you will the quality will decrease. So what we can do about that? How we can manage this problem of the recycle of the water and the water quality? So I will talk about all these topics today. We have been working in all these topics. So in the last 10 years. So let's start by know what is water, what is the difference. And we'll start that this is something that is not new. It has been used in several parts, not only in Chile, for flotation and leaching, for copper and other minerals. And the same in Chile is used for copper, but also for other minerals. And I will show some example also in other areas. But seawater is water with 35 grams of salt. And most of this salt is sodium chloride. So, but the problem is not with the sodium chloride. We will see the problem is with the magnesium and calcium. That is a small amount, but they produce problems. Also, in this other that's here, very low, there are carbonate and borate, and these are also problems in the use of seawater. The first thing is that we have all these ions, but they change because they form complex. For example, if the pH is below A, magnesium will be like ion, cations, but if we change the pH over 10, we will have this magnesium hydroxide, and this will produce problem in the operation. So you can see the component are not just alone, they form different components. And this is one of the problems in the system. But also, because we're going to use this in the ore, there are other components from the ore that will move to the liquid, to the water, and they also will do the same. For example, if we have copper, if the pH is below 7, we are going to have just copper, but over 7, we have all these different components that is formed in the solution. And all of these, or some of them, will produce some problems. The same happened with the iron. The iron in seawater will have different complex, has a function of the pH. Okay, so now that we know what is seawater, and maybe what's some of the problems are, as I mentioned, is magnesium, calcium, and the carbonate and the borate that are in the system. But now I would like to talk a little about the transportation and desalination. So first, already there are several desalination plants in Chile. So these are all desalination plants that are in the year 2019. And the problem is that there are, I think, 2 or 3, maybe 3, they are the more important problems. First, that desalination plant produce a brine, a concentrate brine. And this brine is disposal in the ocean. And that can produce some environmental impact, some local marine ecosystem problem. The second is they will use energy, and the energy will produce some greenhouse gas emission. And third is the problem of transportation. So by now, each company, this is Antofagasta region, we have several pipes in the region that go from the coast to the mountain. And these pipes are also different desalination plants. So there is also a problem with the distribution of this water in the system. So here is an example. This is Radomiro Tomic plant. This is a copper mine. It's located here. And they use desalinated water. So they had to pump from the coast to here. So first the desalination plant, this is the coast mountain, and then they go up to the plant. You see, they had to go to around 3,000 meters over sea level. So the main cost is not the distance because there are only 170 kilometers. The energy to move this is not very high. The problem is that they had to elevate the water, and that is the cost. So the cost of transportation is about two-thirds of the cost, and the desalination is one-third. And the cost of this water is around $5 to $6 per cubic meter. So it's expensive, very expensive. If you compare with the normal plant, is around one. So this is 5 times more expensive. So this is the first issue. And here, another example, this is another mine, Sierra Gorda. They use raw seawater, seawater without desalination. And you see they had also this large pipe to transport the seawater. And this can be done for big companies because they had the money to build all this stuff. But a small company have problems because it become more expensive, the water. You have a small plant and a small pipe to transport. So this can be done only for big companies. So because of that, we start to do a research on water distribution. So when we study what are the advantages of using a network for the distribution of the seawater. So for that, we use optimization, and we demonstrate that, for example, for this problem, that there are several potential desalination plants and several plants. This in yellow are the plant. The optimum system is to have just one big plant, desalination plant, and one system for the distribution of the water. This reduces the cost, but also it reduces the environmental impact because they use less energy in the system. There is less pipe in the region. This is a desert, but there is life in the desert. For example, there are bears that go to the desert to reproduction. And all this pipe in the system produce also problems. So it's there also the landscape it becomes worse with so many pipes. There are pipes also there are electricity to run the pipe. So we can reduce that. So unfortunately, we were on this topic after they already had built several desalination plants. But together with the people for SMI from the University of Queensland, they have a branch in Chile. We work together in other regions. This is the Atacama region. So here in red are the pipe, are the mines. There are a small one that you compare with the Antofagasta. And we studied several possibilities for desalination plant. So we will design, but in this case, we work together with the community and with the industrial. And in here we make several seminars and meetings with people to develop the best network. And so we develop this network for the distribution of the water using only 2 desalination plant. And this is maybe not the optimal that we obtain using the software, but it's the one that the community agree they can be used because they also consider other issues that are difficult to include in the optimization model. So we use the optimization model together with these seminars to be able to develop this network. And this is an example of how we can solve problems for the industrial and solve problems also for the community, because also there are here some water for small towns that also will use this water. So the other problem about desalination is that the reverse osmosis plant will take the seawater, will produce desalinated seawater for mine, also for domestic use. In Antofagasta city, we drink desalinated water. But they have this brine, and this brine is a more concentrated brine, and most of them is go back to the ocean, and this produces environmental problem. So we start to study what we can do with this brine, and so we thought that it can be used to leach another mineral that is called caliche. The caliche is has this composition, so they have this sodium nitrate that are the main component, but also iodine that is not here, but they have carbonate mineral of iodine, and they leach using water. So we study if we can use this brine, and if we can use also seawater to operate this mine. And we got very good results. So here we have a few examples. This is the recovery using the brine from the desalination plant, and this using seawater. Here, this blue one is the nitrate. That is the main component. This sodium nitrate is used as a fertilizer, and this company will mix with potassium chloride to produce potassium nitrate. That is the main product. So this is a very good result if you compare with using seawater. We obtain better result with the brine than with seawater. We are not completely sure, but this brine had also other components because the desalination plant had to treat it to eliminate bacteria, to eliminate components that can precipitate inside of the plant. So this brine is not just seawater, it has also some additive. And we think that these components help to get better result than if we use just seawater. And the same is for iodine. It's here. You can see we got very good recovery with iodine. So we prove we prove that we can use this in this mine. There are some mines that now are using seawater, but not the brine. So we're working with this company to see if we can use finally this brine in the operation and avoid to use fresh water. That is, they use also fresh water. Okay, so how about mineral processing? So what are the problems of using seawater in mineral processing? We try to work on use seawater without desalination to avoid the desalination plant, to avoid the problem of the brine. So most of our work have focused on how we can solve the problems of using seawater in mineral processing. So I will show first the problems. So it's very common to change the pH in mineral processing. For example, to depress pyrite. And the problem is that if we use lime to change the pH, you can see here that if you use tap water, the consumption of brine, the lime is about 2 grams by kilo per kilogram. But if you use seawater, you will need a lot more of lime. And the reason for this is because seawater has a buffer effect. This fat buffer comes for the carbonate and for the borate in the system. So first, you have to use a lot of lime for the buffer, and after the buffer, you have to use more to precipitate the magnesium and calcium will precipitate in the system, and this increase the consumption of lime. So there are some problems to change the pH to depress pyrite, for example, and we change the pH for several reasons in mineral processing. So this is one of the problems. Here we have also problem with the recovery of molybdenum. So this is fresh water. So you can see that this is the change of pH. The copper recovery is okay. Also the molybdenum in red is okay. And what we wanted to do is to depress pyrite. So this is we want a low recovery of pyrite. And if we use seawater, you see that we can depress pyrite, but also we're going to depress molybdenum. And the reason why we depress this is because there is some precipitation of magnesiums, but also calcium sulfate together with the molybdenum. So that decreases the recovery and also decrease the quality of the product in the plant. And actually, the salt in the system can help the flotation. Here we have the recovery of chalcopyrite. This is just distillate water. And you see, if we use seawater, we can improve the recovery of chalcopyrite. This is, there are several reasons why this improves. One of them is that sodium chloride helps to the bubble size, will decrease the bubble size. So we had more small bubble, more bubble means better recovery of chalcopyrite. But for other minerals like the chalcocite, this is also copper mineral, copper ore, the chalcocite will decrease in seawater. Here is seawater. But how we can solve this problem of chalcocite is very easy. We had to use more collectors. So the industry, to be able to have good recovery of chalcocite, they had to use more collectors. They increase the consumption of region. So it's more, they add more costs in the system. But I don't have the graph here, but if you add more collectors, then you will have the same recovery that in distillate water. So this is the case of molybdenum. Just here, this is recovery, natural floatability without collector of molybdenum. And if we add sodium chloride, we're going to increase the recovery. So sodium chloride, like in the case of copper, will improve the recovery of molybdenum if there is no magnesium. But the problem is if you are over these regions in the concentration of sulfate and calcium, if you are in this region, then you start to precipitate gypsum, that is calcium sulfate. So you can see here, this is the concentrate, that there are some gypsum and together with the molybdenum. So we'll reduce the recovery molybdenum and will reduce the quality of the product. That is, if the mineral has clay, there is also problem. So there are some minerals that have high level of clay. So I put this just to remember that we can have very good recovery of chalcopyrite using seawater, no problem. But if we try to recover chalcopyrite using a high level of clay, then if we have magnesium, the recovery will decrease. Also, if we have calcium, it will decrease. So this is one of the reasons that I mentioned that the main problem is not the sodium chloride, because with the sodium chloride we can increase the recovery of chalcopyrite, but it's magnesium and calcium that will decrease the recovery of chalcopyrite if there are clay. But it will decrease also the recovery of molybdenum if there are some sulfate. So the main problem are these two ions in the system. So this is the reason that several companies trying to avoid to use water, they use desalinate water using reverse osmosis. And the one that use raw seawater without desalination, they cannot change the pH. It's a problem. So they use, for example, sodium metabisulfite to depress pyrite. But there are other problems. This is not the only problem about pyrite. So we start to work on how we can eliminate magnesium and calcium from seawater, but not all the components. If sodium chloride is not a problem in the system, why we have to remove it? Why not to focus in magnesium and calcium? And so we have developed two different technology. One is we use bacteria that can precipitate the magnesium. We call this biodesalination. And this reduce the impact and only eliminate these two components. And the other option is we're using carbon dioxide together with some other components to be able to precipitate the magnesium and calcium, and try to also use this carbon dioxide in the system. The problem with the use of bacteria is it have very high cost, CapEx costs, because the equipment are the genetic is slow genetic. And the problem with the carbon dioxide is that we have to use some chemicals in the system. But anyway, in both cases, we can obtain very good results. So here we have copper recovery, molybdenum recovery, and iron that we're gonna to depress. And with seawater, at pH, natural pH, the seawater, we don't have problems. But with the recovery of copper and molybdenum, but we cannot depress pyrite. So we want just to change the pH to be able to depress pyrite. So if we use this pH, I already mentioned, we can depress the pyrite, but the recovery of copper will decrease because of the clay. This is a real mineral. And also molybdenum will decrease. But if we use seawater using low level of magnesium and calcium, we can obtain good recovery of copper, molybdenum, and we're able to depress pyrite. It will operate around 4. It depends on the residence time, of course. So if we eliminate magnesium and calcium, we can obtain very good results in the plant. Okay, this is not the only problem. The other problem with seawater is that it's more difficult to recover the water. The reason for that is the magnesium and calcium ion agents. You can see here, this is the setting time. This is the thickeners operation where we're going to recover the water. So this is the setting time of the particle. You can see that they have very low setting rate in seawater. Here, this is seawater. And this is with a magnesium and calcium solution. So the main problem is the magnesium. And if we use this seawater treated, it will eliminate magnesium and calcium. It will reduce the amount of magnesium and calcium. We can increase the setting rate. And the reason for this is that the flocus, if you see here, the size of the flocus will decrease with seawater. And so if we use the seawater without magnesium and calcium, we have good size. And this helps to have better setting rate. So if we can eliminate magnesium and calcium, we're also going to increase the recovery of water. How I mentioned, it's expensive. So they wanted to recover as much as they can, and it's difficult with seawater. So this is a tailing with seawater. This is Sierra Gorda. This is me, and this is my postdoctoral that work with me in this project. You can see a lot of water. And the reason that is a lot of water is because it's difficult to recover the water. And so they lose water in the system. But there are also good news in the tailing. They had better physical stability. So I don't know if you have been in a tailing, but you cannot work inside the tailing because of the water, and they need a lot of time to be able to have physical stability. Even in the desert, it can take months to be able. But with seawater, after 2-3 days, they are very stable physically. So this is something that is good. And also, that is good, there is not generation of acid mine drainage. We will see that if we use seawater, we don't have this problem. So these are two things that are good for the company because they had less problem with the chemical and physical stability of the tailing. So to prove that, we study the stability of pyrite of the tailing using deionized water and seawater. So if you use normal water, you will have some acid production because the pyrite will oxidize, and this will produce this iron component, and this is very oxidant component, and this will oxidize the other component. So if you have other component in the system, they will leach and they will produce this acid problem in the system. But with seawater, that doesn't happen, and there are 3 reasons that why doesn't the chemical stability. The first one is that it will produce acid because of the buffer effect of seawater. This will be difficult to change the pH. Second, because this iron will precipitate and will produce a coating effect over the surface of the pyrite that will isolate the pyrite from the liquid and avoid the oxidation. And calcium and magnesium ion also produce a coating over the surface. And these 3 phenomena will help to have better chemical stability of the tailing. So here we have different, these are artificial tailing. One had quartz with pyrite, or the pyrite, chalcopyrite, and this is arsenopyrite. So there's also arsenic in the system. And all of these use water, and all of these use seawater. You can see that all the seawater are very stable, the pH. So that means that they not produce acid in the system. So these are tests and all the studies that we have done that show that there's an advantage of using seawater in the physical and chemical stability of the tailing. Okay, so now I wanted to move to a different topic. This is process integration. This is the recirculation of the water. So because water is expensive, the company wanted to recycle the water the most they can. And today they recycle about 70 to 80% of the water. That's a lot of water they are able to recycle. Okay, so what are the advantages of recycle? Well, they will use less fresh water. So this is the main advantage. And they can also show they had low water footprint if you compare with other companies. You know that copper is used for electromobility. And they say electromobility had low environmental impact. But how about copper production? If it have a very high water footprint, that's no good. So company also wanted to show they have low water footprint, low energy use for the production of copper. So in that way, they can say also that the copper in the in the car is also coupled with low environmental problem. But disadvantage, we have a problem with the decrease in the water quality. And because of this decrease in the water quality, they had to add more reagents. So if the system doesn't work properly, they will start to add more and more reagents. And this also can affect the metallurgy result. And most of the company in Chile, they will mix all the water, and they will use this as a processed water. So this processed water will start to have impurity reagents. This because they combine, it can be very different combination. Also, the season can affect the quality of this water, and so it will be some problems. And today, most of the company only care about mass integration. Mass integration means if I have this water available and they need the water in all the place, I can recycle the water. So this is mass integration. But they do not consider, it's not consider the quality in this, only the water. So because this is now a problem, we start to work also in the quality. I already mentioned that there are problems. So what are the problems in the water? The calcium, magnesium, sulfate. It can also be some problem with the copper ions that can activate pyrite. Also, it can be problem with the pH. The level of oxygen in the system will also affect. There are several issues about the water quality. So I wanna talk a little about mass and integration, because these two concepts are well known. So when we talk about integration, it means that there are some streams that have energy available, and there are other streams that need this energy. So any integration means to transfer this energy from this stream to this other stream, so we can reduce the amount of new energy that comes to the system. The same is the case of mass integration. So if we had water, for example, in the dam, in the tailing dam, and we need water in the rougher, we can transfer this water, and we will do mass integration. And these two concepts are easy to use because they use this material and energy balance concept that say that all the mass and energy input flow stream must match or equal to the output stream. So we can apply this balance to apply this energy and mass integration. But when we talk about quality, we're talking about property. And if we had good property here available, and we need this property here, and we need to transfer property, will be very nice. But property cannot be applied like the mass and energy balance. We cannot make property balance. So there is a problem if you wanted to use property integration. So we are using some work available in the literature that allow to do that, and this mathematical description that I'm not going through, that allow to change this property in a new operator that can be used as a additive property. So we can, like the energy and mass, we can add and rest property. And so we decided to apply this to a flotation plant. For that, we first had to define what are the properties that we wanted to take care in the system. Then we had to define what are the values of this property that we want in the system. And then our objective was to establish operation region, to establish a way that we can study different way to do this mass integration, including property integration. So these are the steps. First, we have to establish what are the maximum and minimum value of the property that we want to study. Based on that and the string that we can construct a region where we can operate, and then we have all the conditions about this cluster calculation and AUP property that can is mathematical transformation only, and if I show the equation, look very complex, but are not such complex. So what we can do with that? Each property, if we change the property to this cluster property, can be represented in like this. And this yellow region shows the region where we can operate. And this region comes from the maximum and minimum value of the property that we wanted to use. So we can then mix a string like here, using mass, like a mass balance, but with the property to see if we are inside or outside of this region. And there are a second condition that is related to this AUP property that had to be between a minimum and maximum value. So this is a condition that comes from the value of the minimum and maximum property, but also from the mass flow rate in the system. So this is the plan that we studied. It is a plan in Antofagasta region for copper. So basically, we had a grinding, then we had a rougher step. Here comes the tailing. Then we have two cleaner and two scavenger for this cleaner. And from the tailing from this second scavenger also go to the tailing. And this concentrate has some energite. So the mineral are chalcopyrite, energite, bornite, chalcocite, and cobellite. Energite is a copper and arsenic component. So this is a problem with this, with the arsenic. So this roaster is to purify the concentrate and to eliminate the arsenic in the energite component here. And if we see the water, we have some water that come from the thickeners, or the water comes from the tailing dam. And from this stage of the purification, we have this roaster water, and they combine all this water in just one pool. It's the process water pool from where the water is recycled to the system. So this is the plant. So we went to the plant, take sample from different part of the process, and so we sample basically the concentrate, the tailing, and the feed of all the stage. We also sampled all the tailing water, so we have here the tailing water, the thickener tailing water, and this processed water is the mix of all of this here. And of course, we have fresh water. And we measured the sulfate, some calcium, magnesium, copper, and also the pH and conductivity, several properties in the system. So these are the values that we obtained. And we define, in this example, we're just going to use some value from the literature. We wanted to have this property between some minimum and maximum value that are here. So, for example, we wanted to keep magnesium between 0 and 2.43 milligrams per liter. So this is the concentration that we allow in the system. And so where this minimum, maximum value come from? Well, it depends on the plant. You have to study where the best conditions to have good recovery, not to have problem with the water recovery, that it can decrease the amount of reagent that you use in the system, all these issues that are important in a flotation plant. And just I wanted to show few examples here is the possibility if we have the rougher feed and we mix with the tailing water, will be inside of the region. In this case, we have the magnesium, copper, and calcium property. So for this case, it's okay to operate. And if we see this other condition, this is the rougher, this is the tailing water, and the mix of this is here. So it's totally feasible to use this tailing water for the rougher stage. So that means that, for example, we can have a different water pool just for this to recycle this water here and obtain better property in the rougher if we use the process water pool that we already are using in the plant. There are several possibilities. Here is, for example, for the cleaner, we can use the roasting water. It's okay for the cleaner, and so this is the, let me see, this is the feed to the cleaner. This is roasted water, and we mix together. We are here in the properties, so we are between the minimum and maximum value. So it's totally also feasible to use. So we're using this to study different possibility to study different scenarios of how we can improve the operation of the plant. This can be done also mixing stream. For example, here we have again the rougher, and if we use the water from the dam, we're going to be outside of the region. So it's not possible to use the water dams in the rougher. It's possible, but we're not going to obtain the property that we want. So we'll have to deal with other problems, like add more regions in the system. So we can calculate using this how much fresh water do you need to mix with the dam to be able to be inside of the region. So for this example, we need to about 63% of fresh water to be able, if we want to use the water from the dam, we will need this amount of fresh water. So in that way, we can see that it's maybe no good option to use this water from the dam. But also we can study if we wanted to purify some water, which property we have to change in the water dam to be able to have the property that we want in the plant. So this methodology allow us to manage the water in the system. And now we are working in, because it's a graph method, we're working in the using an optimization technique so we can manage several properties at the same time in one company. So with this, I will finish just a few comments. That the first one is that an integrated seawater generation and distribution system will reduce the cost and environmental impacts of the system. That the best is to use seawater without desalination to avoid the use of energy. But we need to eliminate magnesium and calcium. If we eliminate these two components, we will have good condition in flotation, thickening, and in detailing operation. And finally, these integration tools that we are working on allow us to manage the quality of the water. So to do not only mass integration, but also property integration in the use of water. Thank you.
Thank you, Professor Lee. It's very interesting and very impressive. So since that is much more details that you present that then that in that congress conference in Vietnam. That's yeah. Okay, now that that we have time to that rest some questions. Do some questions? Any questions? Okay, go ahead.
Yes. First of all, I would like to thank Professor Luis to give us this presentation. Was so meaningful for us as students, as researchers. We learn so many things, and before coming here, I try to see your backgrounds. Congratulations, Professor. Your job is very good. Go ahead. And then me, I would like to raise some questions related to the brain. The brain water, like when you are talking about the seawater treatment because of the company, and then the process was using like the reverse osmosis. And this process is very expensive. So I would like to get some insight related to this process about the cost. About the cost in your country on this place that you develop this technology. What about the cost in that area? And then you say you implemented like two processes, like you can distribute the water for the people that are living nearby, and then for the company. And then related to this, there's no risk for these people, like using the same pipe, the water that coming from the sea, and then for the company and then for the population. There's no contamination of the water during this process.
The water that we use for drinking and the water for the company are different. After desalination, you have to add some ions because during desalination you will remove most of them. And for drinking, you need some ions in the system. So if you use the desalinated water for company, they will use just the sweet water without any other things. It will be very pure. For drinking, they have to add more ions. And if you wanted to use for agricultural activity, you have to add different ions because there are different needs in the quality of the water. It depends on the use that you're going to give. There is no risk in drinking the seawater. I didn't mention, but in these regions, when it wasn't desalinated water, they used the water from the mountain. But this water from the mountain had high level of arsenic because when they leach the mountain, the rain leach the mountain, and so this water that's in the mountain is not also good for drinking. So maybe desalinated water is better than they use the other water.
Thank you. And second question was related to the season on your country, on the place that you developed this experiment. How many seasons that there is in this place? Because, for instance, in China, we have like 4 seasons. And then the season have several impact on water too. So related to your country, which one is it can provide like a good water quality compared to other? Thank you.
The problem with the season if you use water is that during the summer you have a lot of microalgae, and so this is a problem in the nature plant. You have to remove all these microalgae. It changes. It depends on the season. We have this. If the water is cold in Chile, but if the temperature increases, we have a lot of this microalgae. So this is one problem. And then the second problem is the evaporation during the summer is very high. So they lose more water in the dam. They have a very high loss of water by evaporation during the summer. So there are some issues. It's not a big change in the temperature during the winter and summer. It's not like the US that were below zero during the winter and over the 60 degrees until the summer. We have less change, but there are some issues also related to the seasons.
Thank you. Luis, no questions. What's the percentage of that the water in that operation cost?
How much is the?
How much is that?
I'm not sure. I don't have it.
You don't have that data.
Yeah.
But you said that it's about
$5 to $6 cubic.
That's in there. You know that I worked in that salt lake. Yeah, that's the price of the water is about $1.5 per cubic meters. So that's that's about $5. Yeah, that's very high.
Very
so
high. Yes.
Very high.
Yes.
Okay.
Yes. It's very high.
Okay. More questions? Someone? Okay.
Thank you for your presentation, Professor. It's very interesting. And in your presentation, you point out that using biodesalination technology to deal with the seawater. So I want to know this technology has been applied in industry?
No, we don't have a. We have a. Right now had a pilot. I don't know if it's called pilot test of the plant, but no industrial application. And yes,
I think that's that research in that project to find kind of the bacteria to only eat that the calcium and the mechanism. This mechanism, and then that you said that that's the harmful the irons in the seawater is that calcium and magnesium. So if we can find that kind of bacteria to remove the two irons, I think that would be very nice.
This bacteria or this type of bacteria have been used for cementation to repair. We also are studying the use for avoid the stability of the rod. This kind of bacteria also can be used because it precipitates the magnesium, and that will be done. And if you are interested, I have quite several papers related to that. So this bacteria come from the Atacama salar. So it's in the mountain. So what we do is went to, let me show them. Yeah. We went around here. There are several salt lake here. Salt lake. This is where the lithium comes from. Okay, and there are small lakes, several small lakes, and in all this mountain, and from there we take samples of bacteria, isolate and study which one work better for that.
Yeah.
Okay. So that's I think that's the time that we just it's 1 hour, but I think that's more than 1 hour.
Yeah.
1 hour. Okay. So that's thank you.
Thank you,
Luis. So that's give us a very impressive and very interesting seminar. So also thanks that all of that in that online that for that webinar. Okay, so finally we brought to that. Thank you very much. Okay. So that's our that webinar that's finished right now. Okay, thank you all.